Hello everybody. Let's revise carboxylic acids and amines today. So let's start with questions. We will understand the important reactions in these two chapters, and with the help of questions, I guarantee that the revision will be thorough. So let's do a good revision of carboxylic acids and amines. In this question, what do we see? Okay, so in the first question you have this acid CH3COOH. CH3COOH is what? Ethanoic acid. After you treat ethanoic acid with SOCl2, you get A. So what is A? You will get A, then after A, you get B. So let's start with A. We know that this OH will be replaced with Cl, which means A is CH3COCl. Okay, next. When CH3COCl is treated with benzene in the presence of anhydrous LCl3, we get B. So what is B? We all know that benzene undergoes Friedel-Crafts acylation. This is what is happening here. Benzene is undergoing Friedel-Crafts acylation. So CH3CO will get attached to the ring, and hence B will be this. This is B. This is B. So B is acetophenone. Now B is treated with HCN. B has been treated with HCN. Okay, let's see now what is happening here. If I treat this with HCN, now a ketone on being treated with HCN gives us a cyanohydrin. Right, so this is C. And now if C is subjected to acidic hydrolysis, we get D, which means this CN will get converted to COOH. So CN will get converted to COOH. So the product will be, final product, that is D, will be this, right? This one. So this is what? This is D. The structure of D would be, we have been asked to identify the structure of D. So which option is it? So C containing CH3 and then OH, COH. Yes, option A. Because the same carbon has CH3, OH as well as COH. Same carbon has CH3, OH as well as COH, right? Okay, next question. The compounds A and B in the reaction sequence are given by the set. Now this is again acetyl chloride CH3COCl. It is being treated with CH3CO minus. See, Na plus is not going to do anything because it is a positively charged ion. CH3CO minus is undergoing the reaction with CH3COCl. What is going to happen if I show the exact mechanism? This is CH3COCl, right? Now if CH3COCl is being treated with CH3 COO minus, this negatively charged species will attack this carbon, and we know that halogen will leave, and hence we will get what? We will get, so this is acting as a nucleophile here, right? And to this carbon I will attach this oxygen O, and then O is attached to CO, and then CO is attached to CH3. So this is A. This is A. CH3C, that means I can write CH3 for clarity, right? So CH3COOCOCH3. CH3COOCOCH3. Okay. Now let's talk about B. So in B, I mean to get B, we will treat this with phenol. Now phenol is what? Phenol is C6H5OH. If phenol undergoes reaction with CH3COCl, again a similar thing will happen here. Phenol is acting as a nucleophile. So this thing is going to happen now. And from this oxygen, this H will go out in the form of H+, so HCl will be a byproduct, right? Hence I will write C6 H5O, and that O will be connected to this C, right, and then CH3. So this is B is an ester, right? So B is what? Phenyl acetate. Phenyl acetate. So option B is the correct answer. Basically, we had to identify the nucleophile. So here phenol was a nucleophile, and to get A, CH3CO minus was the nucleophile. Cl minus has acted as a leaving group. Here also Cl minus has acted as a leaving group. Next reaction. CH3CH2COOH. This is a carboxylic acid. All right. Now see, what do we have here? This is indicating a particular reaction. If you remember, in NCERT it's given Hell-Volhard-Zelinsky reaction. So this is alpha carbon with respect to COOH. I treat this carboxylic acid with red phosphorus in the presence of halogen. I get a compound where alpha hydrogen is replaced with a halogen. In this case, chlorine is the halogen. And hence we will say this is A. Alright. Now from A, we have to get B. This is alcoholic QH. If I treat A with alcoholic QH, I'll get B. Right? Basically, alcoholic QH is what? C2H5O minus. We all know that if alcoholic QH or alcoholic NaOH or NaNH2 is added to a compound which has a halogen atom connected to a 2 degree or a 3 degree carbon, then elimination takes place, E2 takes place, and so I'll get a double bond between these two carbon atoms. I'll remove this hydrogen, I'll remove this halogen, right? So what will be the product? CH2 double bond CH-COOH. So this is the product. So this is B. CH2 double bond CH-COOH. CH2 double bond CH-COOH. So option A is the correct answer. Next question. Correct reactivity order of decarboxylation is. Focus on this word. If you remember, decarboxylation is carried out by using soda lime. So in this reaction, the main point is carbanion. When decarboxylation is carried out by using soda lime, then a carbanion is generated. So the general reaction is this: RCOONA gives us R minus, and then eventually R minus gets converted to RH. Right? So this is decarboxylation, which means this is our area of interest. More the stability of R minus, faster is the reaction. So we can say if I get a more stable carbanion in this reaction, then the ease of decarboxylation will be more. So correct reactivity order. So let's form carbanions now. Right? So we have to form carbanions. Okay. So the most stable carbanion will be obtained in this case, right? That is in this case, third case. In third case, because of NO2, which will have a strong minus M effect. And also here, okay, yes, even here NO2 will have a strong minus M effect. Here NO2 will show minus I because NO2 is attached at meta position with respect to this. Okay, yes. So the most stable carbanion will be obtained in case of 1. Why? Because in case of 1, minus I will also be very strong because of the small distance. That is, here if you see, NO2 is attached at ortho position of COONA. In 3, NO2 is attached at para position of COONA. Minus M does not depend on distance, but minus I depends on distance. Minus M is same in both, right? But minus I is not same in both, and hence minus I is more here. So in 1 we will get a more stable carbanion. After 1 it's 3 and then 2. In 2 there is no minus M of NO2 because NO2 is at meta position. So it's 1 then 3 and then 2. 1, 3, 2. So option B is the correct answer. Option B. Because the most stable carbanion will be obtained if I get a carbanion from 1. Because in 1 minus I will also be very strong because of small distance. In 2, there is no minus M of NO2. Again, I'm repeating because NO2 is at meta position. In 3, there will be minus M, but minus I will be very less because NO2 is very far from this CO group. Okay. Which is most reactive towards hydrolysis? Okay. Now, the most reactive compound towards hydrolysis is the one where the carbon which is having a double bond with oxygen is more electrophilic. That means I'll focus on this carbon, that is the carbon which is having a double bond with oxygen. Greater the electrophilicity of the carbon, higher is the reactivity towards hydrolysis. So if you see in this option, that is in B, NO2 will show a minus M effect. Because again, with respect to this C, NO2 is at para position. Since NO2 is at para position with respect to this C, it will exert minus M. Here nothing is attached to this phenyl ring. Okay. Here we'll have CH3. CH3 shows plus H. Because again, CH3 is at para position with respect to this carbon. Halogen shows minus I. Always halogens show minus I effect. Now, the electrophilicity of this carbon will be enhanced due to strong minus M effect. More the electrophilicity of this carbon, greater is the reactivity towards hydrolysis, and hence B is the correct answer. And the least reactive towards hydrolysis will be A, because in A there is a plus H effect. Plus H and plus M effects will decrease the electrophilicity of this carbon, and hence we will say that reactivity towards hydrolysis goes down if there is more of plus H or plus M. Hence B is the correct answer because they have asked for the most reactive compound. So minus M is desired if I want higher reactivity towards hydrolysis. Whenever we have C double bond O, keep this in mind. Which of the following reagents may be used to distinguish between phenol and benzoic acid? This is a carboxylic acid, this is phenol. Now, if I talk about a reagent which can distinguish, that means if I treat that phenol with that reagent, and if I treat benzoic acid with that same reagent in different test tubes, then I should get different results. Let's say if one reacts and the other does not react, then easily I'll be able to say that yes, this one reacted, so this is something like, let's say this is a characteristic feature of phenol, if phenol is undergoing the reaction. And otherwise, if we say that yes, benzoic acid is undergoing the reaction but phenol is not undergoing the reaction, in that case as well we can say yes, there is a distinction. So if a particular reagent is able to tell me that yes, there is a difference because there is no reaction in one case and there is a reaction in the other case, then we will say yes, that is the answer. So if I talk about neutral FeCl3, then what will happen? We know that phenol, when treated with neutral FeCl3, undergoes a reaction and we get violet coloration. We get a product which is violet in color, so the color becomes violet. Whereas when a carboxylic acid is treated with FeCl3, no such coloration takes place. So I can say yes, neutral FeCl3 can be used to distinguish phenol from benzoic acid. See, NaOH cannot be used for distinction because phenol reacts with NaOH, because phenol acts as an acid when you add NaOH. And also benzoic acid is an acid. When you add NaOH, benzoic acid undergoes reaction with NaOH. Then how can we see that distinction is possible? Both are undergoing reaction with NaOH, right? Tollens reagent. This is used for aldehydes. None of them is an aldehyde, so there is no point. Both of these will not react with Tollens reagent. Victor-Mayer test is used for alcohols. Both of these will not react with Victor-Mayer's sequence. The reagents used in Victor-Mayer test. So only FeCl3 can be used to distinguish phenol from benzoic acid because this will give us violet coloration, and benzoic acid being a carboxylic acid will not undergo reaction with neutral FeCl3, so no coloration will be seen. Acyl chlorides undergo. So what is acyl chloride? This is acyl chloride, right? This is acyl chloride. Now what happens? we all know that if a nucleophile is added to this, then the exact mechanism happens in this way. And immediately this takes place, this process. Cl minus acts as a leaving group, and we get this as the product. Look at this product and look at the initial reactant. Can you see that Cl has been replaced with Nu? We know that if something is replaced with something, that is called a substitution reaction. And the nucleophile has come and taken the place of halogen. That means the nucleophile has attacked this carbon, and in the process this Cl has been expelled. So we can call this, overall it is a substitution reaction, right? And it is a nucleophilic substitution reaction. So nucleophilic substitution reaction. Option B is the correct answer. Nucleophilic substitution reactions. The reaction of ethanol with acetic anhydride is an example of, let's see. So this is ethanol. This is ethanol. And acetic anhydride is this. This is acetic anhydride. A similar thing will happen. This is acting as a nucleophile. This will attack this carbon, and in that process we will get this. O will acquire a negative charge, and here O H plus charge will appear on O because O has given its lone pair, and then CH2 CH3. Immediately this will come back and a pi bond will be formed, and this will act as a leaving group. Also this O will get rid of plus charge, H plus will go out, and so I can say CH3COOH has gone out. Minus CH3COH, that means H plus from here and CH3CO minus from this. So CH3COH has got eliminated, and now we have obtained this, right? Then we have O, this O, and then CH2 CH3. Right? So this is the product obtained when ethanol undergoes reaction with acetic anhydride. So what has happened here? Can I say that if I focus on this compound, it is acetic anhydride, then this portion has been replaced with this portion, that is OCOCH3 has been replaced by OCH2CH3. So again it is a substitution reaction. This was a nucleophile because it donated its pair of electrons, and so this is again an example of nucleophilic substitution. This is the nucleophile in this case, right? Ethanol is acting as the nucleophile. Nucleophilic substitution. This portion has been replaced with this portion. Hence it is substitution. A replacement reaction is called substitution reaction. Since the nucleophile came and attacked the species, we are calling this a nucleophilic substitution reaction, right? I hope it's clear to all of you. So this is similar to this example. That means both acyl chlorides as well as anhydrides, acid anhydrides, undergo nucleophilic substitution reactions. Okay. Next question. The reduction of acetamide gives. What is acetamide? This is acetamide. This is called acetamide. CH3CONH2. Now if you look at this, this contains amide group, AMID, amide. And amide on being reduced by LiLH4 gives us an amine. So this is the product. This is what? This is a 1 degree amine. So a 1 degree acetamide gets converted to a 1 degree amine if you use LiLH4 as the reducing agent. So here this has acted as a reducing agent. You can also write it like this, LAH. Lithium aluminum hydride is the full name of LiLH4. LAH is the short form. Lithium aluminum hydride is the full name. So in general, what can I say? I can say RCONH2 gets converted to RCH2NH2. So what is the correct answer? Option A, right? Option A is the correct answer. Which is used in preparation of aldehyde by Rosenmund reaction. Very, very important reaction, Rosenmund reaction. It is there in NCERT. This reaction is used for the preparation of aldehydes. So what happens? We use an acid chloride or acyl chloride, right? RCOCl gets converted to aldehyde. So this is the exact reaction. Palladium is the catalyst. Hydrogen is the reducing agent. You have to use BaSO4 in order to get the aldehyde as the final answer, and hence this is the product obtained. If you don't use BaSO4, if you just use this, then you get alcohol. So be careful. This is not Rosenmund reaction. This is Rosenmund reaction, right? So this is Rosenmund reaction because we are obtaining an aldehyde. So which is used as the starting material? We are using acid chloride. So option C is the correct answer. So BaSO4 or CaCO3, any of these two is used for Rosenmund reaction. Next question. Which is most reactive towards nucleophilic addition? Okay. So again, same thing. If the substance is coming and attacking some species which has a CO group, then we have to talk about the electrophilicity of this carbon, right? Now remember, electrophilicity of this carbon is very high if you have halogen attached to this carbon. So I am giving you the order. So towards nucleophilic addition, this is the order of reactivities. This is the correct order. You have to memorize this order. So most reactive is acid chloride, and then least reactive is this one, amide. This is an aldehyde, this is a ketone, this is an ester. This is ester. Right? So most reactive is acid halide, hence C is the correct answer. And the least reactive will be A. This is the correct order. Okay, an acetamide on being treated with, or rather on being heated with P2O5 gives us what? So keep this in mind. If we have RCONH2, and if we are treating this with P2O5 at high temperature, then dehydration occurs. So remove this oxygen, remove H2. So you are left with this. So you get a nitrile. This is the product. So this is dehydration. This is dehydration, right? Same logic used for dehydrating carboxylic acids. So B2O5 is acting as a dehydrating agent. P2O5 is acting as a dehydrating agent. So in this question, this is R, right? CH3 is R. So CH3CN. So B is the correct answer. CH3CN is called acetonitrile. Right? So this is nitrile, this is anhydride. In both these reactions, P2O5 is acting as a dehydrating agent. Let's look at the next question. Okay. Very interesting question. Right? Now, if you go back to aldehydes and ketones, then you will be able to solve this part easily. Like if you just try to do a quick recap of reactions of carbonyl compounds, then you will be able to obtain A. So I'm giving you around 15 seconds, work out A. And after A, you can again think about the final answer, but at least reach till A. So I'll give you around 10 to 15 seconds. I want you to solve this because we have discussed carbonyl compounds already, right? It's a very nice question. Done? Okay. So this is an aldehyde. Also, this is an aldehyde. With respect to each aldehyde, if you look at the alpha carbons, then you will be able to arrive at the conclusion. Clearly, there is no alpha hydrogen, but we have used a strong base. And we know that when an aldehyde lacking alpha hydrogens is treated with NaOH or KOH, which is concentrated, we get a reaction called Carney-Zaro reaction. So a very important reaction will take place that's called Carney-Zaro reaction. Now here, both the aldehydes are in the same molecules, so the reaction will be called intramolecular Carney-Zaro reaction. So what is A? So A will be this one, right? So this is A. Carney-Zaro reaction has taken place. The next, after this, if I add a few drops of H plus, then I'll get this. CO minus will get converted to COOH. Right. If I perform esterification, that means if I heat this compound with acid, then esterification will take place. Why? Because I have carboxylic acid as well as alcohol. And since both of them are present in the same molecule, this is intramolecular esterification. So this will be the final product. Look at this. This is CH2, CH2. Okay, this CH2 is this CH2. CO, CO, and then COO. This O is coming from this O which is attached to CH2. So if this O is 18, then I'll write 18 here. This indicates that this oxygen atom in the final ester is coming from the alcohol. That means this is the same oxygen which was attached to CH2. Right? So this is intramolecular esterification. So what is the correct answer? B is the correct answer. Why did I perform esterification? How did I figure out that esterification will happen? See, we have carboxylic acid and we have alcohol. Both of these are present in the same compound. Whenever both carboxylic acid and alcohol are present within the same compound, and if that compound is heated with an acid, that means we have to perform esterification. See, if you go back to the actual esterification, that means the one which you are used to, this is what we write. If you remember esterification, this is esterification, correct? So same thing has happened. So this is the ester formed. Here this is the ester formed. The difference between this reaction and this reaction is that here we have performed intramolecular esterification because both the functional groups are present within the same molecule. Here the two functional groups, carboxylic acid and alcohol, are in different molecules. But the process is same. We have performed esterification. Okay. Next question. The major product formed in the elimination reaction of this is, okay. So this is a 4-degree ammonium part, right? Nitrogen is attached to 4 carbon atoms. So it's a 4-degree nitrogen atom. It's a quaternary nitrogen atom. And whenever we have 4 bonds formed by a single nitrogen atom, then a positive charge appears on that nitrogen. So +1 is the formal charge on nitrogen. Fine. We will mark the alpha carbon atoms. These are the 4 alpha carbon atoms. Alpha, 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 alpha. So there are 4 alpha carbon atoms here. Then beta. Let's mark beta. This is a beta carbon. This is also a beta carbon. A carbon atom which is bonded to alpha carbon atom is called a beta carbon atom. Right. And also this is beta. Okay. Now, coming to the product. Remember one thing, if I have to perform elimination reaction of a species which has a 4-degree nitrogen atom in it, then the final answer is given by forming a double bond between alpha and beta carbon atoms. It is beta elimination. That means I have to remove one hydrogen atom from beta carbon. But the major product is Hoffman product in this case. So we have to keep in mind that when we perform beta elimination of 4-degree ammonium salt or a compound which is of this kind, which has a nitrogen atom bonded to 4 carbon atoms, then we will always report our final answer as Hoffman. That means the major product will be Hoffman product. So let's see what happens here. I mean, we have to form the products now. If I remove beta hydrogen, that is if I remove hydrogen from this carbon atom, then I'll place a double bond between this alpha and this beta. So this is what I will do, right? This is one possible product. This is obtained, right? I'm not saying that this is major or minor. I'm just writing the products formed. Eventually, we'll decide which is major because ultimately we have to say that the Hoffman product is the major product. Okay, what about the other product? Again, beta. From beta, I have to remove. Remember, we have to remove only one beta hydrogen at a time. So this is another product. I have removed this hydrogen atom. So double bond is appearing between alpha and beta, right? Then next one. There is another product obtained because I have this beta carbon as well. So if I now take out one hydrogen from this, then what will happen? Then I'll obtain this as a product. I'm writing here so that it's clear. All right, these are the different products obtained. Now, which is the Hoffman product? I'll have to decide the Hoffman product now. So, the Hoffman product will be the one in which there are minimum alpha hydrogen atoms with respect to the double bond. So, let's start counting. In this compound, how many alpha hydrogen atoms are present? So, we have these 2 alpha hydrogen atoms, right? These 2 alpha hydrogen atoms, okay? Then here we have 3, here we have 3, and then these 2. So 5 alpha hydrogen atoms. Now look at this. Here we have 2 alpha hydrogen atoms. Right. Now, how do we decide? See, when you form this product, you are taking out beta hydrogen from this carbon. When you form this product, you are taking out beta hydrogen from this carbon, right? Okay. Now, this carbon is further connected to one more carbon, that is this one. Whereas this carbon is not further connected to anything else. Which means, for the base, it is easier to remove hydrogen from this beta carbon. That's what we say when we perform elimination of a 4-degree ammonium salt. So we will say this is the major product because the beta carbon from which hydrogen needs to be removed by the base should be very easily accessible to the base. That means it should not be statically hindered at all, which means it should not be attached to groups. So if you look at this carbon, this is not attached to any further group, whereas this beta carbon is attached again to this carbon, right? Hence, this is the major product. So B is the correct answer. So the beta carbon from which you remove the hydrogen atom should not be statically hindered, should be very easily accessible. That means around it there should not be crowding. There should not be crowding at all, right? And if there is crowding, then we will see where the crowding is minimum. The hindrance should be the least when I'm taking out the beta hydrogen atom. So this will be the major product because this beta carbon is not further connected to anything else. So B option is the correct answer. Next question. Which will react with acetone to give a product containing, okay. Now, C double bond N, this is what we need. So this is imine, right? IMINE, imine, substituted imine. Now acetone is a ketone, this is acetone. This is acetone. If I react this with a 1-degree amine, RNH2 is a 1-degree amine, then condensation takes place, H2 will be lost. And I will obtain this as a product. This is what was required, if you see. Which means a 1-degree amine will react with a ketone to give a compound which has C double bond N. And if you notice carefully, then this N does not have any hydrogen atom attached to it. That means this nitrogen atom is coming from the 1-degree amine. So let's search. So option A is the correct answer. This is aniline. This is a 1-degree amine. Aniline, 1-degree amine, C6H5NH2, right? This is a 3-degree amine. This is a 2-degree amine. This is not an amine exactly. This is NH2, phenylhydrazine. This is called phenylhydrazine. If you react acetone with phenylhydrazine, then what will happen? Let's see now. I'll show you the product. Again, the same thing will be performed. You remove oxygen, you remove H2, so condensation happens, and this is the product obtained. Yes, so this will be the product when phenylhydrazine reacts with acetone. Right, so option A is correct because we are interested in something of this sort, where N should be connected to further carbon. When I leave a bond after N, that means it's connected to carbon. Hence A is the correct answer. Next reaction. In the reaction of para-chloroaniline with chloroform in the presence of NaOH, the product formed is, okay, para-chloroaniline. This is aniline. Para-chloroaniline is this. P means para. So para-chloroaniline is treated in the presence of chloroform and NaOH. CHCl3 is chloroform. Chloroform and NaOH are present. Now, any 1-degree amine on being treated with chloroform and base gives us a compound which is foul smelling, and this reaction is known as carboxylamine reaction, and NH2 gets converted to NC. Carboxylamine reaction, right? This is called carboxylamine reaction. And also this is called isocyanide test. Carboxylamine reaction is also called isocyanide test. This reaction is used to confirm the presence of a 1-degree amine. All 1-degree amines will react with CHCl3 and NaOH to form carboxylamine or isocyanide. The compound formed is a foul smelling compound. One more thing, 2-degree and 3-degree amines don't respond to this test. So only a 1-degree amine will undergo carboxylamine reaction. So in this case, I mean the question that we have with us, the correct answer is option C. Para-chlorophenyl isocyanide. Para-chloro, that means the chlorine is attached at para position. So para-chlorophenyl isocyanide. Only 1-degree amines will respond to this test. So in general, I can say that RNH2 gets converted to RNC. RNH2 gets converted to RNC in the presence of chloroform and base. Instead of NaOH, you can also take KOH. Instead of NaOH, you can also take KOH. That doesn't matter. So this is the isocyanide, phenyl compound which has a foul smell. And structure of RNC is what? If I want to show the bonds, then this is how I should show. This is a compound formed. Okay, again we have that case 4-degree ammonium. Okay, so this is 4-degree ammonium cation. And what is the major product formed in the following reaction? So let's identify alpha carbon atoms. These are the 4 alpha carbon atoms. This one is beta, and this one is also beta. This one is also beta, right? So I will get different products. The major product will be the one which has least number of alpha hydrogens with respect to the double bond, and hence the correct answer will be this. This will be the major product. If you see, this has 0 alpha hydrogens, because there is no alpha carbon in this alkene. This carbon is not connected to any other sp3 carbon. Similarly, this carbon is not connected to any other sp3 carbon. So there is no alpha carbon, and when there is no alpha carbon, there is no alpha hydrogen. How did I get this product? I got this product when I remove one hydrogen from this beta carbon. So as I said, when we take out one beta hydrogen, we are supposed to form a double bond between alpha and beta. So this is the alpha carbon, this is the beta carbon, so I am forming a double bond between these two. Hence I get this, and I remove this bond, because when I am forming a double bond between these two carbon atoms, I have to remove this entire thing. That means this bond with nitrogen atom needs to be cleaved. Hence option A is the correct answer, ethene. Next question. Butane nitrile may be prepared by heating. Now what is butane nitrile? This is butane nitrile. Butane nitrile is this. Butane nitrile may be prepared by heating. So if I have, let's say, a halogen in, if I have this, okay, halogen atom attached to this carbon. Now there are 3 carbon atoms here, and if I react this with KCN, in this case SN2 will happen, because Cn minus is a good nucleophile. This is what I'll get, right? So the product will be this one. This is the organic product. Now this is butane nitrile. If I write numbers according to IUPAC nomenclature, then this is what I'll get. This is butane nitrile. Nitrile means Cn, and butane indicates that there are 4 carbon atoms. Now what is this compound? This is propyl halide, right? 1, 2, 3, N-propyl halide. So if N-propyl chloride is treated with KCN, I'll get butane nitrile. So option D is the correct answer. In place of X, you can take any halogen, right? Chlorine, bromine, iodine. So in option D, they have taken chlorine as a halogen. So N-propyl chloride. This is called N-propyl halide. If I write Cl in place of X, I should call it N-propyl chloride. So N-propyl chloride is reacting with Cn minus to give us butane nitrile, and the Cn minus is acting as the nucleophile. Cn minus is coming from KCN. We know that K plus has to be in the form of K plus. K will never be K minus, right? So it's K plus. That means we have Cn minus, and a negatively charged species is a nucleophile. So Cn minus is a nucleophile. The reaction occurs in one step, hence it's SN2. Okay, so D is the correct answer. And this is a major product. Okay, one more thing you have to keep in mind, instead of taking KCN, if I react this with AgCN, then the major product will be this. This will be the major product if I react this with AgCN. Okay, keep this in mind. Okay, next question. This is interesting. It's a part of GOC, right? because resonance structures are there, canonical structures. So which is possible? So now see, this is not possible because if you look at this compound, I mean this ion, nitrogen has formed 5 bonds. 1, 2, 3. 3 hydrogen atoms are forming 3 bonds, and then we have this double bond. This is impossible. Nitrogen can never form 5 bonds. The maximum number of bonds that a nitrogen atom can form is 4. The maximum covalency of nitrogen is 4. Then how can we show 5 bonds in a canonical structure? And hence this is invalid. So 2 is a wrong canonical structure, and we will say that 2 is not an acceptable canonical structure because the nitrogen has 10 valence electrons. Not acceptable means it's incorrect, it's not valid. So we are not supposed to draw this, so this is incorrect. We are not supposed to show resonance between these two. Right? So nitrogen cannot form 5 bonds. Next question. Allyl isocyanide contains how many sigma and pi bonds? Okay. Now, what is allyl chloride? This is allyl chloride. This is allyl chloride, allyl bromide, allyl alcohol. See, if I replace Cl with OH, I'll get allyl alcohol. Now, in this question, they are talking about allyl isocyanide. So, replace Cl with NC. This is allyl isocyanide. Now, sigma and pi bonds need to be counted. So, let's start counting. CH2, CH. This is the structure, right? Okay. Let's count the number of sigma bonds. So sigma, 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 sigma. How many sigma bonds? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sigma bonds. 9 sigma bonds. And how many pi bonds are there? 1, this is pi bond, and these are the 2 pi bonds. So 2 and 1, 3 pi bonds. So 9 sigma and 3 pi. Right? Allyl isocyanide. Next question. Nitrobenzene can be prepared from benzene by using a mixture of conc, that is concentrated HNO3 and concentrated H2SO4. Okay. In the nitrating mixture, this nitrating mixture is what? It's a mixture of conc H2SO4 and conc HNO3. Okay. Then what is nitric acid acting as? Okay. Remember EAS, that is electrophilic aromatic substitution of benzene. So if you remember, we use sulfuric acid and nitric acid to generate nitronium ion. This is the electrophile generated in nitration of benzene. Now how do I get this? So if I have to show you the detailed mechanism, then HNO3 is acting as what? So this is HNO3. This is HNO3, right? This is HNO3 and this is H2SO4. This acts as an acid and it gives a proton to nitric acid. If this gives a proton, then I'll get this. This leaves and I get the nitronium ion. This is how NO2 plus is generated. So clearly you can see that this is acting as a base. Why? Because it's accepting H plus from H2SO4. When this oxygen gets protonated, then only we get this, right? So nitric acid is acting as a base and H2SO4 is acting as an acid. So A is the correct answer. Next, which is the false one? That means which is incorrect statement. The rate of nitration of benzene is greater than that of hexadeuterobenzene. This is incorrect We know that in EAS reactions, C6H6, that means benzene, and C6D6 and C6T6, the rates of these are equal in electrophilic substitution reactions. So this is a wrong statement. They have used the word greater. It's not greater, it should be equal. So the rate of reaction of C6H6, that is benzene, is same as the rate of reaction of C6D6, that is hexadeuterobenzene. So in all EAS reactions, this is nitration. Nitration is also EAS, right? So in all the EAS reactions, the rate of reaction does not change if the isotope is changed. So H, D and T are isotopes, but that doesn't matter, the rate will remain the same. So keep this in mind. Next question. Benzene diazonium chloride. Okay, this is benzene diazonium chloride. This is benzene diazonium chloride. Is reacting with phenol, okay, in basic medium to give us what? Now remember, this acts as an electrophile. This is the electrophile. So diazonium ion, benzene diazonium ion acts as the electrophile, and EAS happens, that is electrophilic aromatic substitution happens, and we get this as the product. We know that this OH is ortho para director, OP director, right? So the product obtained is this. So clearly you can see that with respect to OH at para position I have attached this electrophile, right? So this is orange in color. This is called para hydroxyazobenzene. So option B is correct. Para hydroxyazobenzene. This is orange in color. In place of phenol you can take NH2, that is aniline, and you will get a yellow colored compound that is called para aminoazobenzene. So instead of OH, NH2 will be there. These are called coupling reactions. So keep in mind, instead of phenol, if we take aniline, there also coupling will happen, and we'll get a yellow colored compound, and that will be called para aminoazobenzene. This is called para hydroxyazobenzene. Azo means N double bond N. This azo word means N double bond N. Next question. Strongest base is. Let's draw the structures of these. This is the first one. This is option A, aniline. Para nitroaniline. So para nitroaniline is this. This is para nitroaniline. Meta nitroaniline. And this is benzylamine. Benzylamine. This is called benzylamine. If you look at this compound, in this compound, the lone pair of nitrogen atom is not involved in resonance at all. And hence, D is the correct answer. We know that when lone pair of nitrogen atom is not involved in resonance, basic strength is very high. In each of these, the lone pair is involved in resonance with the ring, with the aromatic ring. This will be the weakest base because even NO2 shows minus M. So this is the weakest base out of these four. So the strongest base is this, and then the second strongest is this, and this is the weakest. Next question. The most basic compound in aqueous medium is most basic compound. Now this is 1 degree amine, this is a 3 degree amine, this is an amide, so this is out of discussion because amides are always less basic than amines. And this is a 2 degree amine. So in aqueous solution, 2 degree amines are more basic or the most basic. So D is the correct option. If you remember, this is the correct order of basic strengths in aqueous medium. CH3 twice NH is the most basic amine, followed by this, and then the least basic is this. This is the order of basic strengths in aqueous solution. Similarly, if CH3 is replaced with ET, that is CH3 CH2, then also the most basic remains 2 degree amine. But now there is a slight change. 3 degree amine becomes more basic than 1 degree amine. So this is the correct order of basic strengths in aqueous medium. This is also the correct order of basic strengths in aqueous medium. Right. So D is the correct option, most basic compound. So 2 degree, 1 degree, 3 degree, 2 degree, 3 degree, 1 degree. ET is what? ET is CH2, CH3, right? This is ET. Ethyl group, CH3, CH2. And CH3 can be written as Me. Me is CH3. Okay. Right? So, we have done revision of carboxylic acids and amines. All of these are extremely important. Whatever we have discussed is very, very important for exams. So, keep studying. Okay, all the best. See you soon. Thank you.